Hello, good morning, everyone, or good evening, wherever you are. So I would like to start by thanking Joel and Robert and Salim for organizing this nice meeting under these very difficult conditions and inviting me here to speak. So I am based to answer Joel's question, I'm based at WITS in South Africa. But right now I'm visiting the third place indicated there, which is the Max Planck Institute for Software Systems, which is in Saarbrücken. I will be here until end of March. So, and I'll explain something about the middle affiliation a bit later. So today, let me tell you about Fibonacci numbers and red digits. So this slide is well known to everyone in the audience. This is Fibonacci. And his sequence starts with 0 and 1, and 0 at index n equals 0, 1 at index n equals 1, and then every term is the sum of the preceding two terms. And this is the first thing that appears in my talk, in the title of my talk. The red digits are the numbers that when you represent them in some digit, in some base, then they look like a repeated digit. For example, in base 10, they are of the form a times 10 to the m minus 1 over 9. And if you write them down in base 10, it's going to be a string of m length m of the digit a, which is between 1 and 9, which is repeated n times. In general, if b greater or equal to 2 is an integer, then I will call base b red digits, numbers which when within base b, they have exactly one repeated digit, which is the digit equal to a. So what about red digits? And there, since Diophantine problems is an important topic of this conference, my talk is going to be about Diophantine equations involving Fibonacci numbers and red digits. Red digits have attracted a lot of interest. For example, for a while at the end of the last century, there was a question about red digits, which are perfect powers. Already, I made a misspelling here, Oblak in 1956, he proved that there are no perfect powers which are red digits if the digit is bigger than 1. So there are no red powers which look like 2, 2, 2 concatenated several times, or 3, 3, 3, and so on, except for, maybe I made a little mistake here, m should be strictly bigger than 1. To avoid the case of the red digits, perfect powers 4, 8, and 9. So there are no perfect powers with at least 2 repeated digits if the digit is strictly bigger than 1. The case a equal 1 has been settled by Bourgeois and Mignot in 1999. There's a little mistake here in this slide, x should be between 2 and 10. So they proved that there are no solutions of this Diophantine equation, x to the n minus 1 over x minus 1 equal y to the n. Under various conditions on the base x, one of the conditions was that it's an integer between 2 and 10. The only solutions for m bigger than 1 are these two ones, 3 to the 5th minus 1 over 3 minus 1 equal 11 square. So 11 square, if we write it in base 3, it looks like 5 concatenated 1s, and 20 squared, if you write it in base 7, it's 1, 1, 1, 1. And without the condition that x is between 2 and 10, the only other known solution of this equation, non-trivial one, so we don't want m equal to 1 and don't want m equal to 2, because m equal to 2, the expression on the left becomes x plus 1, and that could be any number you want. So the only other known solution is 18 cubed minus 1 over 18 minus 1 equals 7 cubed. And it is assumed that these ones are the only solutions of the equation x to the m minus 1 over x minus 1 equal y to the n when m is at least 3. But it's still not known in general. There are many results known by Bourgeois, Ljunggren, which was mentioned in Gary Walsh's yesterday, Maurice Mignot, Preda Mihailescu. But I think in full generality, the problem is still open. Now, what about Fibonacci numbers? Since we are talking about their digits, I will mention a result of Stewart of 1980. Stewart in 1980 proves that if you take the Fibonacci number and write it in base B, Fibonacci number f sub n, then the sum of the digits is at least a constant depending on b times log n divided by log n. Well, his result wasn't that much about the sum of the digits, but it was rather about the number of non-zero digits. So, of course, the sum of the digits and the number of non-zero digits, they are comparable quantities because every digit is bounded. So if you have a large sum, then you have a lot of non-zero digits. Actually, Stewart's result was a bit more general. He shows that if you take two multiplicatively independent integers, like 2 and 3, and you take a large integer, and you write it in base 2 and in base 3, then in at least one of these two bases, the number of non-zero digits behaves like the double log of the number divided by the triple log of the number. So a number can't be short, let's say, can't be written in a compact way in both of these two bases. And this can be stretched a little bit further to bases which are not necessarily integers, like the Zeckendorf representation, which you can think about it as representing a number the best you can as sum of powers of the golden section, non-consecutive power. And if you do that, then since the golden section is of course multiplicatively independent over any other integer, and the Fibonacci number is short in that base, then it must belong in all the other bases. So that's what lies behind that. Computational-wise, the Bourgeois, Chico, and Mignot showed in 2013 that if you look at Fibonacci numbers which are representable as a sum of at most 4 powers of 2, then the largest such is F18. So F18 is 2584, and it's 2 to the 11 plus 2 to the 9 plus 2 to the 4 plus 2 cubed, and that's the largest Fibonacci number whose sum of digits in base 2 is at most 4. For this kind of problems, I believe they use linear forms and logarithms maybe. Now there's other methods, especially by Haidu and Taiwan and their younger collaborators, which basically solve these equations in an elementary way by finding suitable moduli with a very small Carmichael lambda function and working modulo those numbers. All right. Let's see what I click on. Oh, I went a bit too fast. Rep-digit Fibonacci numbers. In 2000, I proved that the largest rep-digit in the Fibonacci sequence is 55. And of course, if you are used to linear forms and logarithms, you immediately notice that Fn is exponentially close to the golden section over root 5, and this number is exponentially close to some fixed number times 10 to the m over 9. Therefore, you should be able to use linear forms and logs and bound immediately all the variables. But I didn't do it in that way. I did it with congruences and quadratic reciprocity. And the result has become popular, and people worked on extensions of it. So I started this with some students. Saul Diaz Alvarado was a student of mine in Mexico 10 years ago. We said, what about if we take rep digits, a Fibonacci number, which is the sum of two rep digits? For this, we did use linear forms and logs. And we found that the largest example is 6,765, which is 6666 plus 99. Then there is Saul. I'm going to mention various mathematicians, but I'm not going to show their pictures. I'm only going to show pictures of people which might not be very well known in this community. So we can also go to K-generalized Fibonacci numbers. There are various extensions of that sequence. The K-generalized Fibonacci number, one of the extensions is to take a recurrence of length K. So you start with some initial values, K of them, and then every next term is the sum of the K preceding ones. And you want to say, what should I start with? You say, let's start with K minus 1 consecutive zeros and the 1. And let's make some convention that we arrange them in time in such a way that 1 is the first Fibonacci number and all the other zeros are in the past. So if you make k equal to 2, you get the Fibonacci sequence. If you make k equal to 3, you get an object that's called the Fibonacci sequence, and so on. Those sequences, they are powers of 2 for a while. You can kind of see, suppose that you have a large string of 0 here. So what's the first guy is 1. The next guy is this one plus a bunch of zeros, which is another one. The next guy is 1 plus 1, which is 2 plus a bunch of zeros. The next one is 1 plus 1 plus 2, which is 4 plus a bunch of zeros. The next one is 1 plus 1 plus 2 plus 4 plus these zeros, which is 8, and so on. So this argument shows that the first, basically, k non-zero values, k positive values are all consecutive powers of 2, except for this one at the beginning, which repeats 2 times. But of course, after about k steps, the pattern breaks down, and you start obtaining smaller numbers than the power of 2. So with those ones, there was a paper of Diego Marquez in 2015, which he did. He proved that the largest rep digit in the Fibonacci sequence is 54. So if take k equal to 3, and then he mentioned that he had searched up to k equal 10 or 15, and he didn't find others. So he believes that if you take this family of sequences and you look at the non-trivial rep digits, by non-trivial I mean, of course, 1, 2, and 4, they are members of any k generalized Fibonacci sequence, and 8 also if k is at least 4. And so every number with 1 digit is a rep digit. But what about interesting numbers that have at least 2 digits? So he conjectured that these ones are the only solutions, the only non-trivial solution. And we proved it with John Bravo, which was a student of mine, and I think Marquez also proved it independently. Then we also, I mentioned the Fibonacci number equal a sum of 2 rep digits. You can also go the other way. You can take the rep digit and write as the sum of 2 Fibonacci numbers. You can even write as the sum of 2 k members of the k generalized Fibonacci sequence, and then you get 2 interesting solutions, which is 777 is the sum between the 12th and the 4th member of the 4th sequence, and 555 is the sum between the 11th and the 8th members of the 6th sequence. And then you have these parametric families. What do I mean by parametric families? 33 is a rep digit, which is 1 plus 32. And 66 is a rep digit, which is 64 plus 2. So those rep digits are sums of 2 powers of 2. And as I said, powers of 2, they sit in infinitely many Fibonacci sequences. So this one is the 1, and this one is the 5th, and this one is the 2, and this one is the 64. And if k is large enough, then you get these parametric families. And these ones are the only ones. There's other variations of it. So what else can you do with digits? Well, we can sum them, which we already did, but we can concatenate them. By concatenating them, just stack a bunch of digits, the same digit together, A1, and then we repeat a different digit, A2. And then we can ask, what about numbers of this form? And this one was also studied together with a group from King Abdulaziz University, led by Adel Al-Ahmadi, and with my younger co-authors Alaa Al-Tassan and Hatun Shuaib. And all the solutions of this Diophantine equation, if you take the nth member of the kth generalized sequence, and you try to write it as a concatenation of 2 rep digits, and you need at least 3 digits, of course, because every number with 1 or 2 digits is like that, then you get this, what are there, 7 interesting examples. The first 3 you might recognize them, 144, 233, 377, they are all 3 Fibonacci numbers. 773 is in the 4th sequence, 2000 is in the 7th sequence, 255 is in the 8th sequence, and 511 is in the 9th sequence. And these ones are the only ones. Well, this is the group. This is us working together. When I visit there, which is a couple times per year, of course this year I didn't go because of the COVID. The idea of proofs. The idea of proofs is, first of all, you need some compact representation of the k Fibonacci numbers. Well, this one is a linearly recurrent sequence. Its characteristic polynomial is x to the k minus x to the k minus 1. And all the way down, you subtract lower monomials with coefficients 1 all the way to the end, up to minus 1. It has simple roots. You notice that all the roots are units. And one of them is real and larger than 1, and all the other ones are in the unit disk. It's the absolute value of z strictly smaller than 1. This immediately implies that this polynomial is irreducible. Because if it wouldn't be reducible, the real root would go with some factor, and then for the other guy, the other factor would have all roots which are algebraic integers, which are all smaller than 1 in absolute value, and of course that doesn't exist. Moreover, if you look at the Binet formula, f sub nk, this one is some function of alpha multiplied by alpha to the n minus 1 plus something else. This is the contributions from the other roots. It turns out that the contribution from the other roots, since you know that the other roots are bounded by 1, this quantity should be bounded, of course, from the general theory of linear recurrences. But it turns out that this quantity is in fact bounded by 1 and not only bounded. So you can, maybe even 1/2. So you can always say that f sub nk is the closest integer to this expression. This f sub k of alpha, it has a nice representation. It's basically a rational function of degree 1. And alpha is the largest root at this point. Because of that, this guy is highly dominant because this thing is small. So if you ask if this guy is, let's say, a repdigit, which is a number of the form a10 to the m minus 1 over 9, you apply immediately linear form and logarithms, and you get a bound on n. The problem is that, of course, this number lives in a field of degree k, and the linear forms and logarithms, they throw in some factor, which is the degree of the field in which the numbers live to a certain power. So this gives you that the max of those things is k to the big O. This is if you have just one repdigit. If you have a sum of them, or if you have a concatenation of them, then you just iterate this process. So you look at the main term, then you look at the subsequent main term, and so on. So this works, and this is what Stewart did. So this works if you find a bounded combination of as many repdigits or whatever you want, it's going to give you bounds like this. Where the big O one, it's going to depend on how many guys you're summing. So if you sum too many of them, you're going to get a large exponent. So you're going to say, okay, fine, maybe you convinced me. If these linear forms, you can prove them they are non-zero and so on, so that the method works. You convinced me that maybe you can bound all of the parameters once k is fixed, but my statements are for variable k. How do you deal with the variable k? Well, there's an extra trick here. The variable k, you deal with it because that root, it's exponentially close to 2. You can actually see that because what is that root? That root is the root of x to the k equal the sum of the previous lower powers of x. If you divide this equation by x to the k, then you get 1 equal 1 over x plus 1 over x squared plus 1 over x cubed all the way down to 1 over x to the k. If you continue this series to infinity, so you write 1 equal 1 over x plus 1 over x. Yes?
There is a question in the chat. Can you see it?
Oh, I was... okay, yes. Well, yes, the same method would work. If it's just 2 repdigits, you can do it. I cannot do palindromic Fibonacci numbers. That I cannot do because I cannot control the length of them. But yes, it is possible to find them by the same method. So basically this formula, as I was saying, it comes from the fact that if you extend that series to infinity, so you write 1 equal 1 over x plus 1 over x squared plus 1 over x cubed and so on. So in the right, you get the sum of the geometric series starting at 1 over x. And if it would be extended to infinity, then the solution is 2, because 1/2 plus a fourth plus an 8 and so on, all the way down to infinity, it gives you 1. But this alpha, it stops at 1 over x to the k. So now you do a little bit of analysis, calculus if you want, maybe the intermediate value theorem or something like that. And it gives you right away that if you stop at the step k and you take the solution that comes from there, then this one approximates 2 with an error which is exponential in k. So now let's go back to our Binet formula where we say that basically this guy is the kth Fibonacci number. This guy I can stick in alpha equal to 2 in the function for f sub k and get a rational number. If you stick in alpha equal to 2, there is actually some simplifications in there. Think that you stick in alpha equal to 2 in here. This goes away and this becomes 1/2. So this becomes 1/2 when you stick in alpha equal to 2. This becomes 2 to the n minus 1 when you make alpha to the n minus 1. And here is the error. But now since n is bounded polynomial in k, and this error is exponentially small in k, it means that if k is sufficiently large, then this still remains an exponential saving. So morally, what you do, you go back to your paper, and every time you apply linear forms in logarithms with this amount, you replace this amount by this amount. The difference now is that you work in Q. You have to prove, of course, that these linear forms are non-zero and so on, but if they are non-zero, then since you have an exponential saving in k, and since all the other parameters are bounded, let's say polynomial in k, and linear forms in logarithms takes logs of that, it gives you that k is bounded logarithmically in itself, so this also bounds k. And after you have bounded k, you have bounded everything, and now you just have to go and do the calculations, which are non-trivial because some of the numbers are large, but this is basically what the model is. You can do other concatenations. A paper I wrote a long time ago in 2005 with Bill Banks. We looked at what about concatenating Fibonacci numbers and getting back a Fibonacci number. And we proved that if you concatenate two of them, the largest solution is 55. And with, I think, the solution for concatenating three of them, we don't know what it is. The point is that this result no longer uses linear forms. This result looks visually the same as the previous one, but it isn't. Because the point is that if you concatenate repdigits, you're always working basically with numbers that have a small numbers of powers of 10. So it's a sum, a signed sum with some coefficients of powers of 10. But if you concatenate Fibonacci numbers in base 10, then what you get signed sums of things which are products between the golden section to some powers and the base 10 to some powers. And if you have at least 3 or 4 of those terms, you no longer can use linear forms and logarithms because you have powers, both powers of golden section and powers of 10. So I believe this one is still unknown if you want something to think about. Well, other people thought about it. For example, Diego Marquez and Alain Tobé in 2012, they said, what about if I put a product of consecutive Fibonacci numbers in this side? And they found no interesting solution. They proved that the only interesting solution, the only solution with m at least 2 is the one that has k equal to 1, which is the 55. Then we looked at this, we said, let's generalize it. We put exponent k in there. And then we found 2 solutions, which are basically the Fibonacci and the Fibonacci solution. And then we decided to do it the other way. This is Johnny Gomez, a student of mine from Cali, Colombia. And his colleague is Maribel Diaz. They were visiting me in Mexico in summer of 2019. So what we said, well, let's look at the Tobé Marquez result, where they multiply products of consecutive Fibonacci numbers in the left being a rep digit. Let's look in the right and make consecutive rep digits in the right. Well, of course, consecutive rep digits don't exist because you cannot, if you add 1 to a rep digit, you don't get another rep digit. But let's put something there so that they look consecutive. So let's say of consecutive lengths. So this one, it's m times, then you take another rep digit, another digit, you repeat it m plus 1 time, and so on. So we also find actually 55, it's interesting that it breaks down as 5 times 11, so it actually fits inside this pattern. So let me indicate a little bit the proof of this one, because the proof of this one is slightly different. It was a reason for me to have Johnny learn the triple L algorithm. And this is how you do it. You start with the prime and you work on this side. Start with the prime algorithm 2 and 5. Let's start with the prime 3. Then what happens is that all those numbers over here, they are multiples. This is a multiple of 10 to the m minus 1 over 9. This is a multiple of 10 to the m plus 1 minus 1 over 9, and so on. Now these numbers, as you go with them through consecutive numbers, every now and then they are divisible by 3. So out of every 3 consecutive rep units, let's say 11, 111, and 1,000, 111, one of them is a multiple of 3. This means that on the right-hand side of the equation, you have at least integer part of k over 3 multiples of 3. So that number is divisible with a large enough power of 3, depending linearly on k. And this must divide the nth Fibonacci number. But the nth Fibonacci number is not divisible by large powers of primes. In general, it's a fixed primes. If it's divisible by a large power of a fixed prime, is that large, almost equally large part of that prime was already inside the index. So this gives you the k is logarithmic in n. Now, once k is logarithmic in n, then you know that the sum in here is short. So it's 10 to the n, 10 to the n plus 1 up to something, but this k is logarithmic in n. So you pull out the powers of 10. So you get that the right-hand side, it's roughly of order of magnitude. Well, you lose 9 to the k, you multiply also by something else, which might be at most 8 to the k. But basically, you can hide all that inside O of k squared. So on the right-hand side, it's 10 to the nk plus O of k squared, and the left-hand side, order of magnitude-wise, is alpha to the n. By order of magnitude, I mean there's some constants in there, so that you can put a constant here and a constant there, so that the number itself is at least as big as that first constant times alpha n, and at most the second constant times alpha n, and so on. So you compare these two guys, and then you say, aha, since k is small, is logarithmic in n, it means that m has to be large. So m has to be at least n over k. Now we go back and we do the same thing, but we do it a little bit better. That is, we keep track of the contributions of the nines, and we keep track of the actual digits. And since the part is small, since k is logarithmic in m, and you factor out this 10 to the n, 10 to the n plus 1, and so on, when you get here a power, a bit like in the slide that was involving the proof of things about f sub n k, Fibonacci numbers in the k generalized sequence, you get an error of the type 1 plus O, 1 over 10 to the n, everything raised to power k, but k is small. So you can get rid of k at the cost of decreasing the exponent in here. And this number a, you don't really know what it is. It's actually a rational number because it has some nines in the denominator. But the point is that it comes from the actual digits that repeat themselves. And the only digits are 2, 3, 4, 5, 6. Anyway, they are all smooth numbers. They are 7 smooth. So a is of the form 2 to the 1, 3 to the 2, 5 to the 3, 7 to the 4. Where some of them might be negative. For example, E2 might be negative. E3 is not even an integer because it also encodes the square root of 5 in here. But the point is that alpha to the n is very close. Oh, wait a minute. This a didn't encode yet the square root of 5. I'll put the square root of 5 in there later. So I'm going to say that the difference between this number and this number is there is some exponential saving between the distance between these two numbers. So with this one, you transform the distance between this number to that number, you divide one of them into the other, and you get a product close to 1. You take logarithm and you get a sum of logs close to 0. And the closeness to 0 is given by this m. M is at most n over log n. And all those guys in here, they are bounded this coefficients in terms of n. And this is what linear forms in logarithms are for. You write down your linear form in log, you show that it is non-zero, just because this alpha is an irrational number. You apply Baker's method, you get some bound on n, and then you have to reduce it. Then when you reduce it, then you have to use triple L, because you just have a long sum. You have 5 guys. Normally you use Baker, Davenport, or something like this if you have just a linear form in 2 things, which is inhomogeneous. If it's homogeneous, we use just partial fraction, just continued fraction. All right. Fibonacci rep units in other bases. So up to now, I just insisted in the base 10. For some reason, I haven't seen much in other bases. Maybe the base 2 also has been worked, because we will mention that, because a rep digit in base 2 is just a Mersenne number. It's in the form 2 to the n minus 1 over 2 minus 1. So it's just 2 to the n minus 1, where n is not necessarily a prime, like if it were Mersenne primes. But regarding the base b as a variable, we can ask, what about the solutions of this equation? Now, of course, m equal to 1 is always a solution, just because 1 is a member of the Fibonacci sequence. If m is equal to 2, then you get the Fibonacci numbers of the form b plus 1, and of course, there are infinitely many b's with this property, all the shifted Fibonacci numbers. What can you say about m at least 3? Now, if you fix m at least 3, then you get f sub n is equal to this function in B. This function is a polynomial of degree m minus 1, and it is known that this has only finite many solutions. For that, you can redo it from scratch, or you can invoke a result of Nemes and Peter of 1986. They have a paper in the Journal of Number Theory in which they classify a little bit more generally. In particular, they classify all polynomials of degree bigger than 1, such that f sub n equal that polynomial of x has infinitely many integer solutions and x. And there are such polynomials, but they are just, in some sense, they are the trivial polynomials. What do I mean the trivial polynomials? For example, if n is a multiple of 3, let's say n is 3k, then you can write f sub 3k as a cubic polynomial in f sub k. It's actually one of 2 cubic polynomials, depending if k is even or odd. You get some changes of signs in there. And the same if k is 5, then if n is a multiple of 5, f of 5k is one of 2 polynomials of degree 5 in f of k. In general, if p is any odd integer, and n is divisible by that odd integer p, not necessarily a prime, just make it odd, then f of pm is a polynomial of degree p minus 1, one of 2 polynomials of degree p minus 1 in f sub n. And basically the results of Nemes and Peter show that these are the only polynomials with the property that f of n equal the polynomial in X has infinitely many solutions. All right, so what do we do when we cannot make progress from a problem? Well, it's easy, just add more equations to it. So let's add more equations to our problem. So let's ask about the basis B, such that there are 2 Fibonacci numbers which are the rep units in base B. And this we could answer. As I said, non-trivial ones. I don't allow 1, because if I allow 1, then it will be 3 of them. But let's throw away 1. So B equal to 4 works. If you look at this rep digit in base 4 rep unit, which is 1, 1 base 4, which is 1 plus 4 is 5, that's a Fibonacci number. And if you look at the next one, which is 1 plus 4 plus 16, which is 21, that's another Fibonacci number. The theorem that we are having is that these ones are, this base B is the only base with this property. I think this paper has been accepted by the Journal of Number Theory. All right, so in the rest of my talk, which is another 20 minutes, all I will do is to give you basically the idea, the proof. There are some steps in this proof, because it combines a lot of things. It combines not only linear forms in logs and reduction methods, but some of the projects I worked with lately, this one in particular and some others, and I'm sure a lot of the audience, the people in the audience which have worked with the Diophantine problem, is that you put your linear forms in logs on it, and you put your reduction methods on it, and so on, and you still have a very large space to search for this. So you get bounds, but the bounds are too big. And it's sometimes you get a bit desperate because you don't know how to reduce them, because they will take years on the computer. So let's see how what got into our proof. So first of all, I can get rid of a small base. For example, the base equal 2. This has been done in many places. I would quote a paper that I wrote with Yann Goujon, Maurice Mignot, and Samir Siksak shortly after the proof of these 3 guys of perfect powers in the Fibonacci sequence. They said, Mignot is they said, what about perfect power, shifted perfect powers in the Fibonacci sequence? That is, you add and subtract 1. And I said, I know how to do that, because if you add or subtract 1 to a Fibonacci number, then because of some algebraic formula, then you get a product between a smaller Fibonacci number and a smaller Luca number. It behaves a little bit like these trig identities that if you subtract 2 sinuses, you get a product between a sine and the cosine. So once you know that that is true, and once you know that the factors that you get from, let's say, fn plus minus 1 are almost coprime, then getting a perfect power inside a shifted Fibonacci number reduces to getting perfect powers inside Fibonacci or Luca numbers. And this is what they had already done. So I'm going to ignore this, the base 2. Also, I'm going to assume that any variable, it's enough large. Let's say up to 10,000, I can do it because n is the index of the Fibonacci numbers. There are not too many numbers like this. I take n up to 10,000. I corner the red digit between two consecutive powers of p. Therefore, now I know m. M is going to be at most the log of the nth Fibonacci number over log 3 because b is at least 3. N is at most this much. So m is at most this much. Once I have made up my mind who is n and who is m, then I know who is b, is the integer part of n to the 1 over m minus 1. And now with these candidates, I go and I check whether the equation b to the m minus 1 over b minus 1 equal fn is satisfied. So I computed, we computed, and we got the known solutions together with another solution. For example, 13 is u sub 3, So in base 3, it looks like 1 plus 3 plus 9. But this one is not in our list of solutions because there is not a second Fibonacci number that's a rep unit in base 3. All right, then we rewrite our equation in two ways. For example, one of the ways would be to just group the big term in here. Nobody would ever do that. You would say, why would you do that when you have all these terms? Why can't you do a little bit better? You just group this one and you neglect everything else. Well, it looks like something ridiculous, completely ridiculous to do it in that way. But actually, this equation was useful for many things. So we got a small linear form in 3 logs, which involves 1 log. If you want to do it correctly, you would say, aha, let's do it correctly. Let's put this b to the m over b minus 1 there. If you do it in that way, of course, you get a much better linear form. The drawback of the much better linear form is that this linear form involves 2 logarithms that depend on b, but of course it keeps the exponential saving, whereas this linear form involves only 1 logarithm of b, but it doesn't keep a linear saving. It only the exponential saving. It only gives you a saving in terms of b. Now you want an estimate of n in terms of b. That is easy. You go to Mathématiques thing. You say that this linear form is non-zero. This is very easy to justify. Therefore, you can get a lower bound on it. Alpha is a known number, is the golden section, and m is smaller than n. And here you get some exponential saving in n, and the linear form will throw you 2 logarithms of b in there because of these 2 numbers. So you get that n is at most 10 to the 13 log of n log square of b, and you don't know who b is. And then you try to save on b. Now, in order to save on b, what we are going to do to bound b, we are going to prove, first of all, some ridiculously large astronomical bound on b, and then we'll reduce this bound until we'll get something reasonable. To reduce it, I go to the useless linear form. This is the useless linear form that has only 1 log b. And the idea of this linear form is that I have 2 of them. I have 2 solutions, one with n1m1 and one with n2m2. And they're both small in some sense, where the smallness is given by 1 over b. And there's a theorem of Loxton. The theorem of Loxton says that if I have 2 linear forms which are independent, which you can assume that they are, then instead of the linear, then the smaller of them is bounded, if you take the bounded from below by the exponential of minus a constant times log of the maximum exponent and so on. But the constant, the dependence on the heights, which is usually the product of the heights of these 3 numbers, gets replaced by the square root of the product of the heights. And this one involves only 1 log b. So if I have 2 linear forms that involve only 1 log b, and I apply the simultaneous form of Loxton, then I get a constant depending on the square root of the logarithm of b, which I am comparing to the logarithm of b. And because of that, I can win, and I can write down some bounds. So let's suppose that. Suppose for simplicity that b is not a power of 5, and this one is actually a linear form of rank 3, because these 3 numbers are, if b would be a power of 5, which is rank 2, and you can also do it when b is a power of 5, but I just want to explain the idea. If b is not of a power of 5, then this one, these 3 numbers are multiplicatively independent. I write a second one, which is linearly dependent over the first one, and then I apply Loxton's theorem. Here's what Loxton's theorem says. Suppose that you have S linear forms, in the same logarithm, suppose that these numbers are multiplicatively independent, and suppose that those forms are linearly independent, and take these bounds for the heights. This paper of Loxton is so old that at that time people were working with the actual naive heights, which are the absolute value of the bound, the coefficient of the minimal polynomials. And B is, of course, an upper bound for the coefficients. And then take this height in here. The linear forms at that time had another logarithmic factor, which is, well, it complicates a bit the game, but not in a significant way. This is the saving I was talking about. Instead of having omega, it has omega log omega to the power 1 over s. And this one is the log of b, which at that time was log of b omega, and it has this astronomical constant in here, 16t to the 200t, where t is the number of guys, which for us is 3, and d is the degree, which for us is 2, and so on. So we use this linear form of Loxton. Suppose that b is really 6, therefore gamma is at most log cube of b. I know that b is at least 10,000 because I already did computations in the small range, the degree is 2, and I write down all these things, and I get this one. It comes from the fact that the two linear forms are small, and this is what Loxton tells me, and this is a dreadful number, but it has logarithm of b to the power 1/2 in there. And I had already bounded n logarithmically in b in some previous slide. So everything bounds b. And let's see what do we get. We get that log b is less than log square of n times double log of n cubed. And what did I do? Now I replaced 10 in 8. 8 is that formula that was giving me a bound on n in terms of the logarithm of itself and the logarithm of b. Let's see, maybe it doesn't blow up. And then I get n is at most 10 to the exponent 4,850 log 15 and so on, which after some algebra leads to b. Here's b. b is at most the exponential of 10 to the 2,425. Well, what about that? Well, it's not so bad, actually. It's the problem is anything that is effective and that you can actually write down, continued fractions will take care of it. Let's see how we do that. I replace that in the estimate 8. I get n is at most 10 to the 4,816. And this is where I start my game. My game is at 10,000 for 10 to the 4,868, and log of b is at most this one. Well, in the 80s, there were even published papers that would look at Diophantine equations, and they would write down bounds like that, and those would be in the theorems. They would say, this is the theorem. All the equations are bounded by these numbers, and then we stop there. But that was a game you could play then. Now you cannot play this game. Now we are a little bit more ambitious. We want to compute everything. So then what you do, you eliminate the log b. The point of this bounds, if you have just one log b, and try to go back to it, the point of the worthless bound, this worthless bound, which doesn't seem like much, it's useful in many ways. The fact that you only have one log b in there and you have two forms, this allows you to eliminate this, and you get some form, log of alpha and log of root 5. Even if this b is astronomical, let's say 10 to the 10,000, that only means that you have to compute its first 50,000 convergence or something like this. And Mathematica will compute it. It's, the computers are good nowadays. Oh, what am I doing here? Click something and then, all right. This is it. So I take this linear combination of guys, and I say that the linear combination of guys is at most this one. It's at most this one, let's say. And so we have log 5 of, you can prove that this one is well defined. For example, the denominator is not 0 and so on. So this represents some rational number. So you have the distance between a rational number and this one, which is bounded. And then you can start chipping away at b. You can start getting better and better bounds. For example, you know that n is at most 10 to the 4,868. So if you assume that b is bigger than 10 to the 10,000, roughly 10 to the 9,800, then if you go back to the previous slide, this expression in here is going to be smaller than 1 over twice the square of that number. And because of some well-known fact, the theorem due to Legendre, it means that the fraction in the left is a convergent of log root 5 over log alpha. And you can even say which convergent it is. You can't say exactly which one it is, but you can bound its range because you use the fact that the denominators of the convergence, they grow at least as fast as the sequence of Fibonacci numbers. And 10 to the 4,868 is smaller than the Fibonacci numbers of index 23,300. So all you have to do is to compute the first 23,300 convergence. You take the AIs to be the convergence of log alpha, log root 5 over log alpha. The maximum one that Mathematica finds in this range is 42,618. And because of the sum theorem, this allows you to invert the inequality and say that this distance, it's really not much larger than the maximum of the A's times the square of that. So this basically gives you a much better bound on B. So if you do that, then you get that B was smaller than 10 to the 9,750, which contradicts the assumption that it was bigger than 10 to the 9,800. So think of what we've done. We've done amazing progress. We started with log B at most 10 to the 10,000. Then we got that B is at most 10 to the 10,000. You just do this 2 more times. That's all it takes. And you get B to about 10 to the 50 and N to about 10 to the 18. So this you say, oh, okay, these ones are more reasonable. But from here on, in order to achieve further progress, the situation is not so easy at all. We still have quite a lot of work to do. So what we did, we got rid of some of the annoying B's. For example, some B's are annoying because, for example, we have a solution with n equal 2. So we have B's of the form of Fibonacci number minus 1. And some B's are annoying because they are too small. For example, they are 3 or 4. And some B's are annoying because they are powers of 5 and things like that. But all these numbers, you already know that B is at most 10 to the 50. So there's not too many Fibonacci numbers up to 10 to the 50. There's only 200 of them. And then powers of 5 again, there's not too many of them. There's maybe 100 of them or less. And for each one of this, you go to this equation. Now you know what B is, because even if B is big, the problem is not how big it is. The problem is how many of them they are, because for each one of them, you have to apply Baker-Davenport. So if you select a small bag of B's, then you can apply Baker-Davenport on that. So you get rid of those guys. And then all these Baker-Davenports give you that N2 is at most 500. This is why we climbed up of 10,000 to begin with, just to get rid of small cases. From now on, you assume that B is not 3, 4. It's not the shifted Fibonacci number. It's not a power of 5 and so on. And that N1 is at least 10,000. Then you subtract the two guys, the two good forms. So you get rid of, let's say, log B minus 1 over root 5 or something like this. And you get again a continued fraction guy. You get a very good approximate. I mean, think about this one. B to the M1 is about alpha to the N1, and alpha to the N1 is about alpha to the 10,000. Well, now, anybody who has done computations with continued fractions knows that this is not reasonable. And knows that every B you would give, this would be false. The problem is that you have up to about 10 to the 50 B's, and you cannot do 10 to the 50 B's. You can do about 10 to the 10. So now the game is try to find some algorithm that would not go down from 10 to the 50 to 10 to the 10, but would partition the set of possible B's into lumps of about 10 to the 10 of them. And for each one of them, you can apply this. Because what does it mean to apply this? You apply this convergent trick, and then you write down formally what it means, that the distance from this rational number to log P over log alpha should be at least 1 over the square of the denominator times ak plus 1 plus 2, where ak plus 1 is the number that appears in the continued fraction. And you say that this one is at most 17 over f 10,000 times m2 minus m1. And what this gives you, it gives you that if actually there is a solution like that, then log B over log alpha, somewhere in the first 100 convergence of log B over log alpha, you should get an A that is bigger than 10 to the 2069. Then, of course, you're not, for any B, you can do this computation instantly, and this will be provable false for any fixed B you have. But the problem is that you have too many B's. So now the game is, how do we get rid of the B's? Well, there are various things you can use. For example, you can use a linear form of New York. That helps you a little bit, It helps you in the sense that it lowers the value of M2 to about 2.5 times 10 to the 11. Which you say it's good, but it's, as I said, I want 10 to the 10. I don't want 10 to the 11. 2.5 times 10 to the 11 is already 25 10 to the 10s. And for 10 to the 10, I'm already going to work for about 2 weeks at it. So I don't want 25. So then the following result is useful. If I take a common divisor of M1 minus 1 and M2 minus 1, then it will divide also M2 minus M1, and it will divide also this expression, and I cancel it. Then I get really a very good approximation of the number M2 minus M1 divided by dB. So you see this, and the very good approximation means that the error is at most M2 minus M1 over 1.9 dB squared. So what this kind of statement is trying to say, suppose that I know something about M2 minus M1, and I know some divisor D of it. Then this one should somehow tell me that B is small, or that B is definable in terms of that. So I use this lemma to reduce the upper bound over B. So I divide by this D, which is a common divisor of M2 minus 1 and M1 minus 1. I write down something like this, and then I can compute the max of these AIs from the continued fraction, and I get a bound on B, M2 minus M1 over D. So I said that M2 minus M1 is, let's say, at most, let's say 10 to the, let's say M2 is at most 10 to the 10. Then if D is let's see what does this give me. If I take D equal to 1, I get B is less than 10 to the 24, and then I get M2 is less than 10 to the 11. So already I got 10 to the 11 from 2.5 times 10 to the 11. Now suppose that M2 minus M1 over D is less than B over 2.1. Then what I can do, I can take the number Y, which is M2 minus M1 over D. I compute the closest integer from Y times log root 5 over log alpha. I'm going to call that number the number x. And then I'm going to compute the expression x over y log alpha minus log of root 5 to the power negative 1. And I'm going to compute one of the two closest integers to that. And this is my b. So basically, m2 minus m1 over d computes b in two ways. And since m2 minus m1 is up to 10 to the 11, this means that if d is at least 10, this number is at most 10 to the 10, and this is my bag of 10 to the 10 dBs that I have to apply that to. And I am happy with that. What about the smaller d's? Well, for the smaller d's, I'm going to write down an equation. Yeah, I'm going to finish in a minute. I'm going to write down a smaller equation. I'm going to subtract 1 from both sides. And I'm going to use the factorizations of these fni minus 1s. And I'm going to use the fact that m1 minus 1 and m2 minus 1 are in here. And I can take GCDs of things. So when I take GCDs, this b survives in here. And I get this expression. And when I take GCDs, I get a much smaller expression, like b to the d minus 1 over b minus 1 is roughly the product of 3 or 4 small Fibonacci or Luca numbers. And now I know that b is at most, let's say, 10 to the 50, and d is at most 10. So this means that all these indices are small. And then I do this, and I get a bag of another, let's say, 10 to the 10 possibilities. So this is what I wanted to emphasize. I wanted to emphasize not only the theoretical method, but also the way we did these calculations. And that's all I had to say. Thank you.